Hi, I'm Raghu. This is chapter 4, 5 patterns, 5 trade-offs. This is the same model but different architecture, which causes totally different failures. That's the whole chapter. It's not about which model you pick, it's about the decisions you make around it. 5 decisions, 5 ways things break. Let's walk through each of them. The first one would be the react, reasoning plus acting. Agent thinks, acts, observe what happened, thinks again, loops until it has an answer. Notice this, the max step exit node. Every pass through the loop, the step count goes up. Without the node, nothing in the architecture decides when to stop. The model doesn't have a concept of I am done. It generates the next token. Termination is something you have to build in. So what happens if you don't build it in? Counter goes up, model keeps going, no exception. This ran for like 47 minutes in a real system before monitoring killed it. The developer thought the model got confused. It didn't. It was doing exactly what it's built to do. The architecture just never said stop. Let's see it. Here's the working React agent. So it ran, found the answer, and stopped. The max steps here are 5, is right here. When it hit step 5 with no finish signal, raises loop limit error. The architecture closes the loop because the model won't. Now the failure version. No limit. Same prompt, same model. The only difference here is the failure version, no limit. Same prompt, same model. The only difference is one line, the loop bound. That's the entire difference between a production incident and a working system. Next topic we'll be going into plan and execute, the next pattern. A plan is a frozen snapshot. Correct when it was made, then the world moves on and the plan doesn't notice, right? So what makes this nasty? The executor finishes normally, no crash, no exception. Just the wrong answer from an outdated assumption. Silent failures are always harder to catch than the loud ones. So, wait, let me just show you the cell output here. So, clean version, planner makes a plan, executor runs it, matches. Now, watch if I do the an intervention here by the inject world state change. I call the inject world state change mid execution to simulate a file path changing while the uh, while the plan runs. The executor finished, no error, but it's still using the old path, the one from the plan, not the one that actually exists now. If you weren't looking carefully, you would never know it was wrong. So this is the plan and execute pattern. The next pattern would be the reflection pattern. Pattern 3 is the reflection pattern. Generator produces something. The critic evaluates it. Generator revises. You get progressively better output as long as the criteria are coherent. That as long as is doing a lot of work. If the criteria contradict, like be concise and cover everything. The loop has nowhere stable to land. Pass 1 is concise. Pass 2, the critic says that it's missing stuff. The pass 3, it's concise again. This goes on forever. Every output locally passes. The loop doesn't know when, no, it's going in circles actually. So here's what surprises people. The loop isn't broken in any way it can see. Each iteration produces output. Critic says pass, revise. But the loop has no memory of prior outputs. So it can't tell that iteration 3 looks just like iteration 1. The oscillation is invisible from inside. You have to add that memory from outside. Let's go to the working version first. So, coherent criteria converges in 3 passes, done. Now the same loop, now the same loop with contradictory criteria, maximize brevity and if you see here, maximize brevity and include all detail. Flipping two states, this the fix is a hash set tracking prior outputs. If it produces something it already produces, it know it's cycling. Raises oscillation error, not a model fix. Memory added to the architecture. Now, this is the reflection agent. Now, let's go to the multi-agent collaboration. Before I get into multi-agent, I want to show you something that happened while I was building this chapter because it's actually the clearest example of what this whole chapter is arguing. Here's what the AI gave me. It framed the multi-agent failure mode as prompt confusion between agents. The idea that agents misunderstand each other because the instructions are ambiguous. Fix the prompts and fix the problem. I rejected that because that's a model level explanation, and if you accept it, you'll go fix the prompts and the failure will come back in a different form because you haven't touched the thing that actually caused it. The real failure is coordination deadlock, and it's architectural. It comes from the handoff protocol, not from what the agents say to each other. A perfect way model with perfectly written prompts still deadlocks if the architecture allows circular waiting. The protocol is the problem. Rewiring prompts doesn't fix a protocol, right? So that's the chapter argument, and that's why I rejected the framing. So So how does multi-agent work? You got a pipeline. Researcher produces content, hands to writer, writer to reviewer. Can reviewer can kick back to researcher. Each handoff is designed by the protocol. Deadlock happens when agent A holds a resource waiting for B to release something, while B holds something waiting for A. Neither can move, both doing exactly what the protocol said. That's what makes it architectural. The agents are correct. The protocol is broken. What shows up first is actually a timeout or no output. That's the symptom. Underneath is the circular wait, and underneath that, no resource ordering rule in the hand of spec. You have to go all the way down. Stopping the timeout treating a, is like treating a fever without asking why it's there. The clean pipeline first. Researcher, writer, and reviewer. Done. And here's what happens when I call the create deadlock. Let me show you. If you see here, I call the create deadlock. Both agents called acquire method on a shared lock before either called a release. One ordering rule prevents this entirely. But finding that in a real system means knowing which layer to look at. And that means understanding what you are actually debugging. So this was the multi-agent pattern. The next would be memory augmented agents. Let me show you here. Last pattern, this is the agent pulls from a memory store, uses what it retrieves as context, then generates a response. Really useful for anything stateful. The validation gate sits on the right path, checks records before they go in, but once something is in the store, retrieval bypasses the gate entirely. Whatever gets retrieved goes straight into the context window. Valid, stale, adversarially crafted. The agent doesn't distinguish, it trusts its context. That trust is the vulnerability. Two ways to build the gate. Gate A approaches Let me show you here. Gate A checks structure. Is this a valid record format? Then gate B checks structure, where it came from and how old it is. Both will pass a well-formed record. Only gate B will catch a well-formed record that came from an untrusted source or that's been sitting there past its expiry. The clean retrieval here. Trusted source, valid output. Now I inject an adversarial record, valid schema, wrong provenance. Gate A sees valid schema, lets it through. The agent just answered using injected data. Output looks totally normal. That's the scary part. The gate B checks provenance not from a trusted source, raises context poisoning error. Agent never sees the record. One gate decision, one gate design decision. That's all it is. Like completely different exposure. Let me go to a summary table here. The five patterns, five decisions. Five patterns, five decisions. Every failure here was unpredictable, not from the model, but from the architecture it ran inside. When something breaks, the instinct is to blame the model. 9 times out of 10, the model did exactly what the architecture allowed. Start with these five decisions. Which one was missing or wrong? That's usually your answer as well. Chapter 5 is where it gets interesting. What happens when you combine these patterns? React, inside, plan and execute, reflection, wrapping, multi-agent. Do the failure modes stack or cancel? The diagnostic lens you built here is exactly what you need for that. So